in the on state drive currents are higher magnitude in magnitude compared to bottom contact, and that is what started. I mean, that is how the our interest in contact resistance started, and we further tried to investigate this. So these are the output characteristics of BGTC and BGBC MOSFETs. So both output and transfer characteristics showed that BGTC is having a better or reduced contact resistance. So what we did is we actually, to be honest, the conventional transmission line method in some cases gives erroneous result. So what we did is, because the conventional transmission line method says R total plotted against channel length, so you will get the intercept value as the contact resistance. But what we are missing out in this is that these different channel length devices are actually different devices, and those different devices may have variability in their threshold voltage and mobility. Okay, because we are fabricating different devices of different channel length. So because of these variabilities, the graph that we are plotting, in that the sometimes the data points are not well aligned, and the if we try to fit a line, this intercept sometimes even comes negative, which does not have any physical significance. So what we did instead is we normalize this by writing R total into W by L. So we multiply W by L all across. So it is called width by length normalized total resistance and width by length normalized contact resistance. And what we did is we plotted this W by L normalized R total against 1 by L. Okay, if I am plotting against 1 by L, it is the slope which is going to give the contact resistance and not the intercept in like the previous transmission line method. So this modified transmission line method was we found that it is much better in terms of estimating the contact resistance accurately, and in fact we did some kind of statistical analysis also in terms of the accuracy, and we found that this is much more accurate compared to the conventional transmission line method. And because whatever mobility and threshold voltage variations are there, that is now taken part in the that gets embedded into the constant now, because the slope is now the contact resistance. So with that, we then plotted the R total width by length normalized graph with respect to the channel length or 1 by channel length, and from that we estimated the contact resistance. And we found that the contact resistance was much higher for the BC. You see, two orders of magnitude higher slope. Okay, in the case of BGBC compared to BGTC structures, and then we try to explain, this is what the statistical analysis I was referring to. Then we try to explain these results, and in fact we also did some numerical simulations, and through the current flow line graphs, we could see that actually it's the interface region from which the charge carrier. So this is the top contact structure. This is my organic semiconductor layer, and these are the bottom contact source drain electrode and the organic semiconductor layer. So what we found is that in the bottom contact, actually the charge injection and extraction is happening at through a very narrow area compared to top contact. Top contact, the entire area below the most of the entire area below the source and drain electrodes are actually injecting or extracting the charge carriers. So because of that, the contact resistance is also dependent on the interfacial area through which injection is happening. So we found that it is mainly because of the large interfacial area that the top contact structure offers, that you have a much lower contact resistance in these kind of devices compared to the bottom. Okay, so shall I finish? Okay. So I'm sorry, still there were several things I would like to touch upon, but due to lack of time, not. So anyway, if you have any questions from the portions that I have discussed,
So, thank you for the nice presentation. Actually, I do not know anything about the organic semiconductor devices, but from this particular presentation, I understood many things. So, thank you for that. Just one simple question I want to ask you, sir. Just before 30 to 40 years, there was no LED who can generate blue light. So after that, Suzy Nakamura, he is the scientist, Japanese scientist. He invented the gallium nitride semiconductor devices who can generate blue light. Because of that, the RGB, red, green, and blue, all the three lights we can generate. After that, by combining them, we can generate white light. So for that, the gallium nitride, the band gap is 3.4 electron volt. Now that much of high band gap was almost impossible to generate. That's why the problem was there. Now you told that since the organic photovoltaic cell also can generate lights, and the band gap energy and the mobility also you told that it is around 10 square times electron volt per centimeters per volt second, isn't it? So with this less amount of mobility, how that much of bigger band gap can be generated? Can you please?
band gap has no relation to mobility, first of all. Okay, band gap has a relation to what we call as intrinsic charge carrier concentration. So if I have a higher band gap material, my intrinsic charge carrier concentration will be less. Okay, so that is there, but it has nothing to do with mobility as such. Number one. Number two, if you see most of the organic semiconductors, they have in the band gap corresponding to typically in the visible part of the spectrum and IR. So in fact, very much into NIR is also challenging. But so what happens is with respect to organic devices, organic LEDs, blue is possible, even green was possible, red was possible. That is how you ended up developing OLEDs.
That means we have to just control the numbers of nodes, isn't it? If the numbers of nodes will be increased, then the energy level.
No, but the LED that you are talking about, gallium nitride. So in the inorganic semiconductors, it is rather challenging to get UV the LEDs which are actually emitting UV or near UV or deep UV emissions, because deep UV LEDs are very important for various scientific applications. So that is a little bit challenging. So and the other thing is because if you see, first thing is um, there is this blue LED, there is UV LED. So gallium nitride will end up giving you something like a UV LED. Okay. So important is with the organic semiconductors, you will not be able to get into the UV. Most of the organic semiconductors will not be going into UV. Okay, so you are mostly restricted in the visible spectrum. Little bit you can extend up to NIR region. That is, at max can go up to 850, 900 nanometers. So this is the wavelength range which you are having with organic materials. Inorganic, most of the even silicon or other things, they are unable to give emission. Okay, so you are left with choices to certain extent, zinc oxide or I mean some other oxide semiconductors, and then gallium nitride. But these semiconductors come with their own issues, because you have epitaxial growth taking place, and you have to take care of the lattice mismatch and several other things. Okay, so the way you grow gallium nitride layers is the process is very different, and you have to understand all those things before you can develop anything. So of course, but what exactly was your question?
My question was that band gap, higher band gap, how can we achieve with the help of organic semiconducting devices?
Higher band gap, you cannot go into UV with organic semiconductor. In fact, I would put it in bluntly that if you illuminate organic materials with UV, especially in the range of below 300 nanometer. Okay, that is typically going towards UVC, UVB or UVC band. Typically, these materials will die out because those in Corona times, people purchased UV sanitizers in homes. Even I purchased. Okay, so anything that I was bringing from outside, I was putting. So this UV light, especially 254 nanometers, that lamp, UV lamp is coming. It is coming very cheap. So you can even build it in your home. So you might have seen that sterilization so basically, most of the organic materials, because living cells, bacteria, these things, viruses, their DNA, DNA is also essentially a carbon molecule. So the carbon-carbon bond is cleaved if you supply energy of UV, and that is the principle on which it works. So there is, if you expose for let's say 30 seconds, 1 minute, so the you end up denaturing their very basic DNA. So that's the whole idea. Any inanimate object you can put it in that sterilization chamber for 30 seconds, 1 minute, and then take out. And even if there was a virus, it is gone. Okay, so most of the organic materials cannot sustain that kind of weakness, so they will not be giving you UVA rays or UV emission. And even you cannot have UV photodetectors based on. So, in fact, that is the whole idea. For different applications, their different materials are suitable for different applications, and that's why so many different research directions are. Any other question?
So, thank you for your valuable insight in this topic. So, if I can use your expertise, sir, my question is from the fabrication point of view. Sir, when we try to deposit this soil gel in a substrate, we come across, I came across especially three issues like cracks in the thin film, then viscosity and adhesion with the substrate. So, sir, can you suggest any solution for this? Any reagents that we can use?
So which material and what exactly are you doing? I will have to look into that. Then only I can come.
Generally, metal oxides.
Okay. So one thing is, you see, why does crack come? Okay, so one or two essential aspects that you should bear in mind is, one is the surface energy of the surface on which you are trying to develop these films should be well managed. So, especially if you are using, because soldier is also essentially a solution-based technique. So, since it's a solution-based technique, the you have to look into, and most probably, if you are using a soldier technique, you are essentially looking into aqueous media, right? It must be in aqueous media. So, in that case, your surface should be hydrophilic. So there are ways to, if your surface is not appropriately, basically your surface energies should match. So that is where the analysis by of the surface by this contact angle method is very critical, because that helps in understanding what is the surface energy of the substrate and what is the surface energy of the next layer that I am going to deposit. So if they are well matched, then those kind of things will not come. And then, of course, you have to be a little careful about maybe you are annealing at a higher temperature than required. So you can change that as well. So that those two things are important for ensuring this thing. And besides that, for improving contact, sometimes some kind of texturing of the substrate also helps in improving the contact. But I'm not sure what applications you are looking, because sometimes texturing can deteriorate your device performance. But texturing is one thing that is surely likely to increase your adhesion. And in our lab, we do laser-based texturing of the substrate. That is possible. So we have Nd:YAG laser. We have several different lasers using which we can do texturing of the substrate.
So that means if we texture the surface, then uniformity will not be there. Or
So again, no, it's not that uniformity will not be there, but as I said, certain device applications you are okay with the texturing. If for certain device application, it may not be a good option. So that you have to choose appropriately. But please try to ensure that your surface energies are well matched. So if you ensure that, then that should not be a problem. And also check the annealing temperatures that you are using. So probably those two things should be able to help you. Any other questions? So I guess the audience, especially those who are not from this background, were able to absorb some of the things that I discussed today. And I hope that probably you would be more interested to read on these topics. And if some of you are interested to do research and or maybe do PhD, so most welcome. So that is one thing I always the purpose of giving such talks is, of course, one is to try to communicate about whatever recent findings we have with respect to our research, but also try to attract right kind of students to do research. Okay, so that is the other side of it. So if anyone is interested to, or if somebody you know would be interested, please refer them to our group. You can find my group's website on ITINDOS homepage. And yeah, that's all. Thank you.
Thank you, sir. Thank you for your valuable insights. You have covered a lot of topics, and definitely I hope that we all learn something from your